Thanks very much. So I've just put a URL up here. This just contains my handwritten notes for the lecture. So I don't promise that they'll be super useful, but it's some kind of record of what I'm going to say. And I'm going to pick up where Patrick left off. So Patrick discussed how to construct a map from R to T in the setting of weight 2 modular forms. So R here was a kind of global deformation ring with a kind of geometric condition at P, and T with the Hecker algebra. Acting on weight 2 modular forms. Okay. And this was a surjective map. So you can think of the spectrum of the Hecker algebra as a closed sub of the spectrum of the deformation ring. And well, the purpose of the rest of our lectures is to explain how you go from here to proving that R is isomorphic to T, or something close to that. And the method is called the Taylor-Wiles method. And the way it works is we're going to compare these two objects by allowing ramification at some auxiliary sets of prime numbers called Taylor-Wiles primes. So we're going to sort of enlarge T sub Q. Q is going to be this set of auxiliary primes. We're going to enlarge the set of Hecker eigenforms we're looking at. So that means we're going to look at a bigger Hecker algebra. We're going to see some more Hecker eigenforms. And on the Galois side, we're going to sort of enlarge the kinds of Galois representations we're looking at. So that means we're going to allow some ramification at these auxiliary prime numbers. And this whole picture will be taking place inside some auxiliary space, which is traditionally called the spectrum of R infinity. And the advantage of this space was that we'll sort of know in advance maybe that it's irreducible. Or maybe even better, we might know that it's smooth. Right. And then I sort of started drawing a picture. So the cube is this ambient space, the spectrum of R infinity, where everything is going to sit inside there. I've drawn the spectrum of T. That's this sort of one-dimensional subscheme. It's finite over ZP. Right, and then we're going to enlarge things. So the idea is, as we adjoin different sets of auxiliary primes Q, we'll get more Hecker eigenforms, which means we'll get more components in this picture. So maybe the purple one is going to be what I get when I join my first set of auxiliary primes. And then maybe I choose a different set and I get kind of some more. So this red one. Let me just drop the specs for now. The red one will come from TQ2, where we're allowing ramification at a different auxiliary set of primes. And then, well, something that's a little bit surprising is that you can somehow take a limit of this picture and show that these Hecker algebras will fill out the whole of this ambient space. So in the end, we'll get that some limit of TQs fill out the whole of R infinity. And once you've done that, you can then go back to this original setting where we had no ramification at auxiliary places and deduce that R is isomorphic to T. Okay. So that's the kind of picture. The whole sort of problem here is we want to show that the Hecker algebra is big enough to see the whole of the deformation ring. And we're going to do that by passing to some limit where we'll sort of force the Hecker algebras to fill out the whole of this auxiliary space. Okay. So this is the sort of sketch of what's happening. This will get sort of executed in lecture 4 with some details. The goal for today is to explain a bit more about these Hecker algebras and about this process of allowing ramification in auxiliary primes on the Hecker algebra side. Okay, so this side of the picture is what I'll talk about today. And we sort of decided to work in a fairly general context. So we won't just talk about modular forms. We're going to follow Caligari and Geraghty and talk about things coming from automorphic representations of GLN over a number field. So that will be the kind of context that we're working in. All right, so I have to start with a bit of setup for that context. So we're going to be looking at hospital automorphic representations, it's CARS for short, of GLN of the ideals of F a number field. And we're actually going to look at sort of cohomological automorphic representations. So they're going to show up in the singular cohomology of some locally symmetric spaces. So section 1 is about locally symmetric spaces and their cohomology. Okay, so just for sort of notational convenience, I'm going to look at an algebraic group over rationals, which is just for restriction of scalars from my number field F to Q of GLN. Okay. So that's a group. I'm going to have a sort of level subgroup for my automorphic representations. So that's a compact open subgroup of the finite adelic points of G. Okay, and this group is just a restricted product of GLN of the completions of F at finite places V, and I'm going to assume that my level subgroup factors as a product of compact open subgroups KV inside these local groups. And at all but finally many places, KV will be the maximal compact you get from looking at integral matrices. That's for almost all these. Good. And now I can define my locally symmetric space. Well, this product lives inside a restricted product because their KVs are equal to these compact opens almost everywhere. My locally symmetric space is kind of double quotient. So if you've seen these before, it will be very familiar. If you haven't, I'll give some examples in a moment. So I have to quotient out by the rational points of G at the end, which is just GLN F. And then I have my real symmetric space, which is a quotient of the real points of G by positive reals kind of embedded in the center of this group. And then there's a maximal connected compact subgroup, K infinity circle. And that's just a product of SONs and UNs, special orthogonal unity groups, depending on the signature of the number field F. And then there's the finite adelic part, where I'm working modulo my level subgroup K. Okay. Do some labeling. So this Archimedean part is what you could call the symmetric space X infinity. And then we take this product with the adelic thing, and then you quotient out by this action of GQ. If K is sufficiently small, GQ will act freely on this product, and you end up with a nice manifold at the end. So we'll always assume that K is sufficiently small. So this is just some real manifold, locally isomorphic to this manifold X infinity. Okay. Write down some examples. So here's sort of 3 key examples to just follow along with as we go through the lectures. So the first one where you can just really write down explicitly what's going on, maybe using class field theory, is going to be n equals 1. So we're just looking at GL1 over a number field F. Okay. Let me record the signature of this number field. So it has R real places and S complex places. Okay. And then it's a nice exercise to look at this definition of the locally symmetric space in this example. So what do we get? In this example, xk is an extension of a finite ray class group by a torus of dimension r plus s minus 1. And well, from the appearance of the integer r plus s minus 1, you might guess that this has something to do with Dirichlet's unit theorem, and that's what you can use to see this. Okay, so this is a sort of sensible manifold that's going to tell us something about number theory as well. We see these ray class groups in the connected components of this manifold. All right. Next very important example is going to be GL2 over Q. So that's going to put us back in the setting of Patrick's first lecture. So for example, if we choose our level subgroup appropriately, it's a thing usually called U1n, then this locally symmetric space xk will be the modular curve of level gamma 1n. So that's a good example. We're just going to recover modular curves from looking at these adelic double quotient spaces. And then final example I'll sort of say things about in particular is where we have GL2 over an imaginary quadratic field. Okay. And then if you look at the symmetric space X infinity, what you get will be isomorphic to SL2C modular SU2. So this is a nice sort of classical symmetric space, so hyperbolic 3 space. And then when we look at the locally symmetric spaces xk, we'll get just like when we look at modular curves, we see quotients of the upper half plane by arithmetic subgroups in SL2R. Here we'll get quotients of the hyperbolic 3 space by arithmetic subgroups in SL2C. So for example, this gamma I could be a congruent subgroup inside SL2 of OF, the integers of our imaginary quadratic field. Okay. So those are the sorts of manifolds that we get when we do this double quotient xk. But maybe the really important thing is that when we look at the cohomology of these manifolds, we're going to see things to do with modular forms and automorphic representations. So that's what I'll discuss next. K infinity is a maximal compact subgroup. So it's just going to be a product of special orthogonal groups and unitary groups. That's why in the GL2 over Q case, we're going to see something like SL2R mod SO2 when we look at this quotient. So that's going to give us the complex upper half plane. Okay, something about cohomology. Okay, so I've got this nice manifold. I can look at its cohomology computed with singular cochains. Very nice thing is if I do this with complex coefficients, then this is closely related to automorphic forms. So this cohomology group will be computed by automorphic forms. And you make the connection by computing this cohomology group using differential forms. And if xk was compact, it's not too hard to see that you can compute these spaces using automorphic forms. In general, xk won't be compact, and it's a hard theorem of Franke, but you can still compute these spaces using automorphic forms. Okay. Something a little bit easier than Franke's theorem is a theorem of Borel. Which says that cuspidal automorphic representations contribute to these cohomology groups. So inside this cohomology group of xk, I'll see some direct sum over cuspidal automorphic representations of GLNAF with a particular local factor at infinity. So pi infinity will be weight 0. That's what tells us that these automorphic representations will really contribute to this cohomology with trivial coefficients. And in the GL2 over Q case, this is just saying that modular forms of weight 2 are what we see when we look at degree 1 cohomology of a modular curve. Right, and then how do these automorphic representations contribute? Well, there's some, you take the finite part of the automorphic representation, you look at its invariance under our level subgroup K. So if that's 0, sometimes this will be 0, and then pi won't show up. But there'll be a finite collection of pi's where this space of invariance is non-zero. And then it will show up in this cohomology group with some multiplicity. So let me write plus mi here. This is some multiplicity that depends on the degree of cohomology you're looking at. But I think it's independent of pi.
Why?
I didn't say that. I just said the cuspidal automorphic forms give us a subspace. We just see a subspace of cohomology here. There's some other stuff. Yeah, so this is just going to give you the cuspidal part of the cohomology. Thanks. Yeah, that was going to be my next remark. Yeah. I'll come to that in a moment. Yeah. Thanks. Yeah, so I should say something about when these multiplicities are non-zero, which I will do next. So this comes from what's called Clausel's purity lemma, from Clausel's article in the Ann Arbor proceedings. Oh, this reminds me. Vincent Poloni asked me to advertise Clausel's birthday conference. It's happening in September. That's all I know. No, there's lots of good speakers. I know that as well. Okay. Yeah, so here's another part of theorem 1, which, as I said, is due to Clausel. So what happens? So each pi here, well, to have a chance of contributing to this cohomology group, it has to have a non-zero space of invariance under the level subgroup. Once you know that, you know the exact range of cohomological degrees in which pi contributes. So there's a very important range of cohomological degrees, which will appear again and again. So it runs from Q0 to Q0 plus L0 inclusive. And maybe the super important thing for us over this lecture course is going to be the range of degrees, the length of this range. So that's L0. So this is sometimes called the Taylor-Wiles defect. And we'll see in Patrick's next lecture, we'll see how this defect appears on the Galois representation side as well. Okay, so what are these numbers? L0 is a difference in ranks. So we've got two real Lie groups here. One is the real points of G. One is the maximal compact of that real Lie group. So we have this difference of ranks. And then I also, when I define the symmetric space, I took this quotient by our positive reals. So that means we have to subtract 1 here as well. Okay. So that's a number. I'll tell you what it is in our 3 important examples in a moment. And then Q0, I mean, you can write down a formula, but the important thing to remember is it makes this range symmetric under Poincare duality. Contributes means the MIs are non-zero. Exactly. Thanks. That's part of the statement. Yeah. Okay, I'm going to talk about these examples, so let me leave A and B on the board. Okay. So in this case, n equals 1. We're looking at cohomology of some torus up to a finite group of connected components. So it's kind of easy to compute its cohomology. And you'll see that what you get is that sort of range of degrees where characters of a class group kind of show up in this cohomology group is just from 0 to degree r plus s minus 1, dimension of our space. So things spread out in all the degrees. Okay, good. That was easy. GL2 over Q. And this is not too hard. We know from Aika-Shimura that cusp forms contribute to degree 1 cohomology of modular curves. So here we'll get Q0 equals 1. So we start in degree 1, and that's the only degree where we see cusp forms. So L0 equals 0. So importantly, this is a case where the sort of Taylor-Wiles defect is 0. So that means the sort of Taylor-Wiles method, as originally written, is going to work in this situation. So in this case, the multiplicity is 2, right? We know that each cusp form contributes to that degree 1 cohomology with a 2-dimensional space. Okay, and then of the imaginary quadratic field, if you look at these relevant Lie groups, you'll see that we end up with Q0 equals 1 and L0 equals 1. So we have things in degree 1 and degree 2 of cohomology. All right, so that's the numerology in these examples. Say again, sorry. GL2 over C. GL2, I mean, this is GL2 over an imaginary quadratic field. I'm always looking at GLN over a number field in the setup.
Right?
Cuspidal, everything is a car, cuspidal automorphic representation. Yeah, exactly. So these degrees are where the cusp forms contribute. Exactly. Yeah. Okay, let me now talk about Hecker algebras or Hecker actions. Yeah. We'll see. Yeah. In the end, maybe it's not a defect. It makes everything work somehow. But yeah. It's also, I mean, there's a more representation theoretic way of thinking about L0, and it's the sort of defect from having discrete series representations, from the real Lie group having discrete series. So when L0 equals 0, you have discrete series. And I mean, for that, maybe I should set things up with semi-simple groups. But anyway, it's something like this. Okay. Hecker algebras. Right. So we're going to fix a set of places S, just like in Patrick's talk. S will contain our sort of places over our favorite prime P. And whenever V is not in S, our level subgroup will be this hyperspecial maximal compact GLN-OV. So S is the places where we're allowed ramification. And again, as in Patrick's talk, we're going to have some p-adic coefficient rings. So that will be E over QP, finite extension. I think E has been used in maybe every talk, and it's slightly different. So yeah, for me, E is a finite extension of QP. Its ring of integers will be O. Its residue field will be K. Its uniformizer will be var pi. Okay, and then what we can do is make the spherical Hecker algebra at places away from S act on our cohomology groups. Just like in the case of modular forms, where we had these Hecker operators TL and SL, to generate the spherical Hecker algebra of GL2QL. Okay, so we're going to have this sort of abstract Hecker algebra, T away from S. So this is a tensor product over places V not in S. And inside that tensor product, you have the spherical Hecker algebra. H with coefficients in O, or coefficient ring. So this is bi-invariant, compactly supported functions on GLN-FV, bi-invariant under this maximal compact. So this is the usual spherical Hecker algebra, which we can understand using the Satake isomorphism. Good. And these Hecker algebras act on the cohomology of our symmetric space. So now I'm going to do things with p-adic coefficients, because we're going to be interested in things like congruences modulo powers of P. So I'll look at the complex computing the cohomology of this manifold with coefficients in O. So this is in the bounded drive category of O modules. And there's a natural way of making these Hecker operators act on this object in the derived category, where that just means there's a algebra homomorphism from TS to the endomorphisms of this thing. So if you don't like these sort of total derived functors, maybe you could just approximate this by thinking of the Hecker algebra acting on the cohomology groups individually. You don't lose very much from thinking about that. And also in the case of GL2 over Q, we'll see in a moment that we can actually just think of the Hecker operators acting on degree 1 cohomology. We just have one interesting degree of cohomology there. So for GL2 over Q, we'll just have a module with an action that's some Hecker operators. Good. And this Hecker action is compatible with the action of the Hecker operators on automorphic representations, which we get if you apply theorem 1. So. If I extend scalars to C along some map iota, then I get some complex Hecker algebra, and that will act on these spaces of invariance in my cuspidal automorphic representations. Okay, so that's this is some big algebra. It's maybe some polynomial algebra and infinitely many variables coming from these different places V. Acting on this nice complex, the image of this map in this endomorphism algebra will just be a finite O algebra. So that's going to be our Hecker algebra T. So we call it TSK to record this level K. It's going to be the image. Image of this big Hecker algebra in the endomorphism algebra. Okay. And this is just a finite O algebra. Finite as an O module. And now we want to do this localization, like in Patrick's talk. We want to fix a sort of mod P system of the Hecker eigenvalues. So that means we're going to fix a maximal ideal in this Hecker algebra with residue field A, just for convenience. If this residue field is bigger, you can just extend scalars. So this will correspond to some mod P Hecker eigenvalues appearing in the cohomology of this locally symmetric space, say with coefficients in this finite field K. So we can rub out mod P because we've already gone to this finite field. So in the modular forms case, that means that we've had a genuine kind of modular form with complex coefficients whose Hecker eigenvalues reduce mod P to something given by this maximal ideal. So in general, that's not exactly what happens because we could have torsion in the cohomology of these symmetric spaces, locally symmetric spaces. So I'll say a little bit more about that when I discuss these examples again. Okay, so we've got this maximal idea in the Hecker algebra, and then we want to sort of localize our module of automorphic forms as well. So do this kind of localization of a maximal ideal M. it will actually just be picking up a direct summand of the original cohomology. And this has an action of the localized Hecker algebra. So this now is just a local O algebra, module finite over O.
But if the endomorphism algebra naturally is complex, wouldn't you want like the Hecker algebra to be a?
I'm just seeing endomorphisms in the category. So it's it's an O module or O algebra.
You can also take the complex itself, like the wouldn't you want? Would it be meaningful to consider another definition of the Hecker algebra?
So that is more or less going to lead to sort of things Venkatesh has thought about to do with derived Hecker algebra actions, where you have things that kind of shift cohomological degrees. So for us, we're just going to think about the image of a Hecker algebra in just the regular endomorphisms. Yeah. So everything has degree 0 as a map of complexes. It's endomorphisms in the derived category. Yeah. I'm very old, so for me, a derived category is just a derived category. There's no infinity categories. It's a category. It's an O linear category. There's a O algebra of endomorphisms.
It gets to the maximal idea is integer.
Yeah, so what does a system of eigenvalues mean? It means you have a homomorphism theta from TSK to K, right? You give me a Hecker operator and I give you its eigenvalue. That's the homomorphism theta. And then the kernel of theta is a maximal ideal. So that's the dictionary between maximal ideals and systems of eigenvalues. Okay. All right, so now I want to say something about when these maximal ideals are non-Eisenstein. So that's something we saw in the modular forms case. And to give a sort of natural definition of non-Eisenstein, it's best to use sort of associated Gauss representations. So at this point, I'm going to assume the first of many conjectures, which I'll assume in this lecture and the next lecture. So here's a conjecture, but it is a theorem of Scholze if F is CM or totally real. So that says that we can attach a mod P Gauss representation to our maximal ideal M. There exists a continuous, semi-simple Gauss representation, which I'll call rho M bar from GF, unramified outside S. With coefficients in K. And well, what does this have to do with the system of Hecker eigenvalues? Well, they're related by the Satake isomorphism. So you just be brief and say that the V not in S, the image of a Frobenius element, its semi-simple conjugacy class is going to be given by N. Then we just say that M is non-Eisenstein when this mod P Gauss representation is absolutely irreducible.
Related with that, those things values doesn't come from negative characters.
Yeah, so here it should have something to do with Hecker eigenvalues that don't come from Eisenstein series, sort of coming as inductions from Levy subgroups in your group, but we're in the sort of mod P setting. So what I just said isn't literally the definition. So instead we give this sort of Galois definition, which for GLT over Q is going to be equivalent to having a congruence to an Eisenstein series. If you were Eisenstein, you would have a congruence to an Eisenstein series. Okay, so let me just write up what I was saying. Rho bar M, absolutely irreducible. If that happens, then we say that M is non-Eisenstein. Okay, and here's another conjecture, which is a version of theorem 1, but with mod P coefficients. And it's about the vanishing or otherwise of our cohomology groups. So this is for non-Eisenstein M. And we're going to assume when we look at just the cohomology in some degree localized at M, that we get 0 if I is not in the sort of special range that I wrote down in this theorem of Varalin-Clauzel. So that's the conjecture, and it's the same kind of vanishing we saw with complex coefficients in theorem 1. And I mean, in theorem 1, we were just talking about the contribution of cusp forms. The point of imposing this non-Eisenstein assumption is that should be sort of saying that only cuspal things contribute here. You just have a characteristic polynomial of the Frobenius element, and it says you can specify what that is in terms of the Hecker eigenvalues coming from M. And to do that specification, you use the Starkey isomorphism. That's right. In the classical modular form case, M non-Eisenstein will mean it doesn't come from Eisenstein series. Okay, so a nice consequence of this conjecture which is about cohomology of mod P coefficients, is that when we look at the total cohomology with O coefficients, we'll get something quasi-isomorphic to a sort of perfect complex in range Q0 to Q0 plus L0. Qi to complex of finite 3O modules in exactly this range of degrees. Okay, so what? It might not come from as a reduction from characteristic 0. Yeah, so I'm about to remark on that when I talk about what happens in my examples. But yeah, that's a good point.
But the finite real model is kind of, there's no deep theory for this, right? The deep statement is the degrees.
Yeah.
Right.
Okay, I'm talking about my examples. GL1, let me just leave it as an exercise to think about what's going on there. GL2 over Q. What's happening? Well, this vanishing says that when we localize a non-Eisenstein ideal, same with our modular curve, that we get something 0. If I is not equal to 1. And that's just because, actually in this case, H2 will vanish, and then H0 is just computed by Eisenstein series. So H0 will vanish in this case. Okay. So in this case, I just have 1. I could do this with K coefficients as well. In this case, I only get 1 non-vanishing cohomology group. H1. And it's a finite free O module. So it's torsion free. That's one way, but you see that this system of Hecker eigenvalues comes from a characteristic 0 modular form. This thing is a finite 3O module. If I invert P, I'll find some Hecker eigenforms. Okay, and what about case C? That's GL2 imaginary quadratic field. So now I have 2 possibly non-vanishing degrees of cohomology. And we have a complex in degrees 1 and 2. Using cohomology. So in degree 1, I'll see the kernel of this map. So I'll get some finite free O module. It's going to be a submodule of a torsion free O module, so it's torsion free again. So in H1, I see something torsion free. And then in H2, I see the co-kernel of this map between finite free O modules. So there I could see a cohomology group which is not torsion free. I'll say more about this on this board. Great. Yeah. In general, this conjecture is super hard, I guess. We don't know so much about it for sort of general L0, but when you have small dimensional examples, it's easy to check. So for this GL2 imaginary quadratic field, in fact, we just have to check that sort of degree 0 cohomology is Eisenstein. And that works in the same way as modular curves. Yeah, so in general, I have to assume this conjecture B, but in these examples, you can just check it. Okay, so what happens in this case C? Let me just write down what I said. So I get a torsion-free O module for degree 1 cohomology. In degree 2, it could have torsion. This is just going to be some finite O module. And the way that I've set things up, it's perfectly possible for H1 to vanish and for H2 to be purely torsion. So in that case, there are actually no characteristic 0 automorphic forms. cusp forms contributing to these cohomology groups. So we're doing something purely in characteristic P. So this is one reason why L0 being positive is a defect. You have this kind of torsion behavior. Okay, but maybe after all, it will turn out to be super interesting rather than being a defect. Right. Yeah, right. You usually expect this torsion to be very big, and there are plenty of examples where indeed you do have vanishing characteristic zero things as well. So you, yeah. So I mean, there's this book of Caligari and Venkatesh that includes some examples like this, which is a nice place to. So this presence of torsion is one thing that makes this construction of Galois representations kind of super interesting. But yeah, I don't have time to say much about constructing Galois representations today. Okay. Right. Oh, I'm going faster than I expected. This is good. Are there any questions at this point? IQF, imaginary quadratic field. The question is, what does IQF stand for? Yeah. Right. Not off the top of their head, but maybe at lunch someone will give you an example. The dimension, the rank of this finite Fourier module. Well, it's the dimension of some space of modular forms where you fixed a mod P system of Hecker eigenvalues. So if you're sort of lucky and you choose n very carefully, then you might get a one-dimensional space. That's right. But in general, in fact, we won't really care what the dimension of these spaces are. I think that must be very difficult to try and compute these dimensions. Yeah, people do compute. I mean, but for sure, yeah, I think people are computing because in the end, you just have to do some computations of cohomology groups for some arithmetic groups. That's one way of thinking about the cohomology groups of these manifolds. They're the same as group cohomology for the fundamental group of the manifold, at least up to the connected components. So if you can compute group cohomology and you can find a presentation of your group, then you can actually compute these things. So yeah, people do that. As a Hecker module, no, I've not said anything about freeness over T. Yeah, you sometimes get that at the end of a Taylor-Wiles method. You can prove that something is a free module over T. But right now, I'm just thinking about whether these are free modules over O or not. Okay.
Do we show
yeah, you have like a Hochschild spectral sequence. So as you shrink the level, you get maybe if you choose a normal subgroup of K, then you get a Galois covering of XK. So you can relate the cohomology upstairs to the cohomology downstairs using a spectral sequence. This will appear at least implicitly actually at the end of the talk. Can I write it explicitly in the case of a complex number field? I'm going to say no, I cannot. That doesn't mean it's impossible. It means at this moment, I cannot. Okay, I'm moving on. Thanks. Good. Okay, and section 3 is going to be about Taylor-Wiles prime. So that's about this question of what happens when we allow ramification at some auxiliary primes. Need to change chalk as well. So if you think back to my picture at the beginning, we want to allow ramification so that our Hecker algebra, or maybe our module of our cohomology group, grows, but in a controlled way, so we'll be able to sort of return back to our original situation at the end of the day. And allowing ramification at Taylor-Wiles primes is the main method we have for allowing this ramification in a controlled way. Although there are other sort of variants you can do as well. Okay, so what is a Taylor-Wiles prime? Well, it's going to be finite place B of F. And there's two sort of important conditions. First is that if you look at the cardinality of the residue field of this place, that's QV. Taylor-Wiles. Yeah. So this cardinality of a residue field has to be 1 modulo some power of P, our sort of coefficient residue characteristic. And well, maybe it's congruent to 1 modulo P to the M. This would be a Taylor-Wiles prime of level M. Okay, that's one important condition. And the other important condition is what happens when we look at our mod P-Gauss representation and evaluate it on a Frobenius element of this prime. Okay, so then I get a matrix, and it's well defined up to conjugacy, and I ask for it to have n distinct eigenvalues. And let's say all the eigenvalues are in K, the field I started with. Okay, and now we're going to, on the Galois side, we'd say that we would allow ramification at one of these primes V. So on the automorphic side, that means we need to change our level subgroup at the place V. So V was not in S. To start with, the level subgroup at V was maximal compact. So we started out with level GLN OV, okay, and we're going to have to shrink the level, use a smaller subgroup. Yeah, M is fixed, and these are sort of Taylor-Wiles primes relative to M. You're saying conjecture A was only a conjecture. Is that what you're?
Yeah, I'm just wondering whether it's so if we're given.
Yeah, we fixed our non-Eisenstein maximum ideal M, which means we're assuming there's this associated residual representation rho bar M.
And then the
Right. So there are two options. You can either just assume conjecture A, so assume it always exists, or you restrict and just work with F, CM or totally real, and then we know it exists. Okay. So those are the two options. Right. Right, we're shrinking the level. So, and let me just write in sort of modular forms world what we want to do. We want to go to maybe something like level gamma 1Q. If Q is our sort of Taylor-Wiles prime. except it won't exactly be this. It'll be something in between gamma 1q and gamma 0q. So there'll be something in between these two subgroups, and that's what I'm going to do here. Okay. Yeah. All right, so first, like gamma 0q, we're going to look at the Iwahori subgroup, IV. This is matrices which are upper triangular modulo a uniformizer at V. Okay. And then the subgroup we want, it turns out actually if we just go to level IV, we won't see any new systems of Hecker eigenvalues. I'll say more about that later, but yeah, actually just going to Iwahori level won't give us anything new, so we have to go a bit deeper. So we'll go to a level I'll call I primed V. I'll define this in a minute, but this is sandwiched in between the Iwahori subgroup and the strict Iwahori subgroup I1V. So I1V is the matrices which are strictly upper triangular modulo V. So that's like gamma 1q in the classical modular form setting. Yeah. Yeah, strictly upper triangular means one's on the diagonal. Okay, and then what happens when I look at Iwahori mod strict Iwahori is I just see something isomorphic to units in the residue field on the diagonal. Okay, so this is a cyclic group of order QV minus 1. That's the residue field of V. And I assumed QV is 1 modulo P to the M. So these groups all have cyclic quotients of order P to the M. So I primed V sort of corresponds to those cyclic quotients. It will be a specific, yeah. So IV mod IV primed is some quotient of this thing modulo strict Iwahori. And I'll move over here, so there's space. This is just going to be the quotient. Here where you take the sort of quotient by P to the nth powers. So you might need to think about the notation a bit to see what we're doing here. But the important thing is that when you look at IV mod IV primed, it's just going to be a P group. You'll have P power order. So it's going to be a cyclic group of size P to the M, n times. Okay, so that's the P group that shows up when you take this quotient. And IV primed is I think it's the unique normal subgroup of IV with this quotient group. Maybe that's some exercise. All right, good. And then this quotient group is very important, so I'll give it a name. It's going to be delta V. Good. And yeah, we should note that if I look at the group algebra over O, because delta V is a P group, O is a local ring with residue characteristic P, this is a local ring. M is the level of the Taylor-Wiles prime, which I think I just erased, sorry, because I got stuck on this side of the room. So QV is 1 modulo P to the M. That's the M. That's why we have these cyclic order P to the M quotients of the units of a residue field. Okay. Shall I swap the boards? Can everyone see? Seems fine. Exactly. Yeah, KV cross is a cyclic group of order QV minus 1. And P to the M divides QV minus 1. So if I do that quotient, I get a cyclic group of order P to the M. Okay, so in a moment, I'll state a sort of precise proposition about what happens when we change the level by going to this subgroup IV primed. Okay. But first, let me just mention why these primes are sensible things to look at. Well, I mean, there's a few reasons, but let me try and say a couple. So we need to allow more ramification, but we need to control that ramification using something. And this action of delta V is going to give us that control. That's going to sort of measure how much ramification we have. So I'll state something precisely, which will capture that in a moment. The other thing to say about this QV congruent to 1 modulo P to the M, well, I mean, it's useful that this ring here is local. Otherwise, everything would just kind of divide up according to maximal ideals. So if you had some other subgroup, maybe normal subgroup, and you looked at the action of the group algebra, if that group algebra decomposed, then the cohomology at that level would decompose as well. And you wouldn't really be building congruences. You'd just be kind of generating new disconnected things. So this localness of this ring is important. The other nice thing about the case when UV is 1 mod P, implies that the Iwahori-Hecker algebra has a very simple structure when we look at it with coefficients in K. So, in general, if you've ever played around with presentations of Hecker algebras or sort of what happens when you multiply together elements in Hecker algebras, you'll have seen lots of Qs appearing in the formulas and maybe even some sort of Q minus 1s appearing. Okay, so when we specialize to Q equals 1, which is a sort of for people who are just sort of pure algebraists looking at these kinds of Hecker algebras, specializing to Q equals 1 is like the trivial case. The whole point of Hecker algebras for algebraists is to do a sort of Q deformation of what happens at Q equals 1. So what happens in that case is you just see the group ring of the co-characters of a torus semi-direct product, the action of a var group, which is Sn in this case. So, Hecker algebras in general might be quite complicated. They have some complicated presentations, Iwahori Matsumoto presentation and the Bernstein presentation. But when you specialize, so it's Q equals 1 case, you just get a group ring. So that's kind of pleasant. Yeah, so you can look at sort of compactly supported bi-invariant functions. It means the coefficient field, yes. And you have a convolution algebra structure on it. Okay. Here's a proposition, and the first part is going to be a precise version of what I said orally, that we won't actually see any new systems of Hecker eigenvalues when we go to Iwahori level. I'm going to assume P is greater than N for safety. I don't think this is really necessary. Part A, the slogan is no new eigenforms at level IV. Okay. What I do, I'm going to look at the cohomology groups I started with. So this is level K, coefficients in O. Localized at my non-Eisenstein maximal ideal. Okay. And this is going to be isomorphic to something at Iwahori level. That means I have to change the level subgroup. So away from V, it's the same as before. And at V, I insert the Iwahori group. Good. Okay. And then I had to localize somewhere. So I could do a sort of localization using the center of the Iwahori Hecker algebra. So I could then localize at sort of an ideal corresponding to M. What I would get then is a whole space of old forms. So if you're familiar with the theory of old and new forms in modular forms, you get every sort of modular form at level 1 will contribute 2 eigenforms to level gamma 0 Q. It's a comma. But that is a very good point. It's a defective notation for sure. Okay. So let me just move. It's a comma, not a prime. Okay, it's the Iwahori group. Okay. Right, in general, you'd see some space of old forms. If we want to cut that down to a one-dimensional space, we did have to do a sort of extra localization. So here I'm going to localize M tilde. So what does that mean? So we're going to add to M. Well, first of all, we maybe need to throw away the Heck operators at V. Okay. But then we're going to throw in some new sort of Hecker eigenvalues. So we're going to say that some suitable Heck operators at level gamma 0 V, let's call them UIV, have to act with a fixed mod P eigenvalue. So this is like looking at a specific stabilization at level gamma 0 Q. In modular forms world, you're going to look for a UQ eigenvector. And you're going to say that its UQ eigenvalue has to be a fixed thing modulo P. And these alpha i's are going to correspond exactly to the eigenvalues of Frobenius under our Galois representation. So alpha 1 up to alpha n are going to be a fixed ordering of the eigenvalues of rho bar from V. So we have these distinct eigenvalues of Frobenius. We can use them to define this maximum ideal in something which contains lives inside the Iwahori Hecker algebra at V. And once you do this sort of localization that says we're just looking at things which are mod P eigenvectors for a specific Heck operator with eigenvalue one of these alphas, then we'll get this isomorphism between things of level prime to V and things with Iwahori level at V. All right.
That's the subset of
Say again? Sorry. M tilde is just a maximum ideal in a slightly different Hecker algebra that acts on here. So I'm not sort of writing it carefully because it just becomes a bit burdensome notationally. But yeah. Over here, we had a spherical Hecker algebra acting at V. Over here, you can make the Iwahori Hecker algebra act at V, or maybe like a commutative subalgebra of the Iwahori Hecker algebra. And this maximum ideal M tilde is coming from the spherical Hecker algebras away from V, plus this commutative thing in the Iwahori Hecker algebra at V. So I'm not writing down full details because it just somehow, at this point in the day, I don't think it would be helpful, but hopefully you get the idea. So there's just some way of doing a further localization here that's going to exhibit the fact that we don't see any new Hecker eigenforms when we go to Iwahori level. Yeah. Yeah. Maybe just the simple roots. I think it's just the co-characters that are like living in sort of they're one in the ith place and zero elsewhere. Exactly. So those Heck operators. Yeah.
and can we see that symmetric?
Yeah, so the symmetric group will move this maximum ideal around. It'll move M tilde to the maximum ideal where you've permuted the alpha i's. So what's going on here is if I just localized at the center of the Iwahori Hecker algebra, what I would see is things coming from n factorial different maximum ideals corresponding to the permutations of these distinct eigenvalues. Yeah, and by fixing this ordering, I'm saying, well, here's just one of those pieces that I'm going to look at. That's K upper V. So that means we're deleting the compact subgroup at, K, at the place V. And we're going to replace it with IV. Yeah. Okay, so we went to Iwahori level and we didn't really see anything new. So now what happens when we go to this level I primed V that I defined over on these boards? Okay. Okay, so we're going to look at the cohomology at level I primed V. Yeah, so there's the prime and here's the comma. Okay. We can still do this localization using the Heck operators U sub V. Okay. And I have an action of the group delta V on this space. So X, K, V, I prime V covers XK, and it's a delta V torso. Okay, so I have an action of its group. So actually I can sort of think about delta V. Well, it's not really a delta V equivariant cohomology it's usually used, but okay, I'm going to look at this cohomology with this delta V equivariant structure. And what I get will be a complex of O delta V modules. Right, so I'm going to remember the delta V action on cohomology. Thank you very much. Yeah. Yeah, the lower one is with Iwahori level. Thanks. The upper one is with this subgroup I primed V. So this is a cover and a torso for the group IV mod I primed V, which is delta V. K needs an upper V. Thank you very much. Good. Okay. So here's my cohomology group. And this is more for psychological convenience than anything else. But when thinking about this change of level, I kind of prefer to work with homology groups instead of cohomology groups. So I'm going to define C lower V to be the sort of O linear dual of this thing. You'll see in a moment why I prefer to use homology. So this is still a rounded complex of O delta V modules. But really it's computing some direct summand of the homology of this space with its delta V action. And we can do the same thing at Iwahori level. And I'll call that empty set because V is about allowing ramification of V. Empty set is when we don't allow ramification of V. So the empty set is the O linear dual of the cohomology at Iwahori level, or by the first part of the proposition, it's the same as doing it at level KV. The same thing as CV, so it's no linear dual of a cohomology, total cohomology thing, except it's at Iwahori level instead of level I primed V. Yeah. Let me just write it. That's the homology of the level we started with, level K. All right, and yeah, when we do this, you already said that the cohomology at level K, or equivalently the homology, C empty set. It's going to be quasi-isomorphic to a complex of finite free O modules in degrees Q0 up to Q0 plus L0. The same thing is going to be true for CV, but now for O delta V modules. You could think about fixing a triangulation at the bottom of our torso and putting that back upstairs. And if you compute sort of simplicial homology with that triangulation, then you'll see that what you get is a complex of finite free O delta V modules. And this sort of vanishing result comes from what we assumed about the mod P cohomology. Okay. And then so the crucial thing is how do we recover things at Iwahori or maximal compact level from what's happening at level I primed V? Well, if I was doing cohomology, I would just have a Hochschild-Sayre spectral sequence, like I remarked in answer to a question earlier. Because I'm doing homology now, I pass this dual, that means I can write that as a sort of Tor spectral sequence. So C empty set, you can just identify with cohomology at level I prime V. And we just do a sort of derived co-invariance tensor over the group ring of delta V with O. Okay, so this identification just comes from the fact you have this delta V torsion. And that's going to tell us how we can sort of go back to empty set of ramification primes from somewhere where we're allowing ramification. We do this tensor down. Good. I'm basically done. What else do I want to say? I have a sort of bigger Hecker algebra acting on this complex at level V as well. We call it T sub V. It doesn't say the cohomology is free. It just says it's computed by a complex where the terms in the complex are free. So this is to do, I mean, one way of thinking about it is you've got a complex over a local ring, and you have what's called a sort of minimal complex, quasi-isomorphic to that. And to understand the minimal complex, you just have to understand the cohomology when you reduce modulo the maximal ideal. And that's the thing we understand using this conjecture B. That tells us exactly about the cohomology with coefficients, mod P. Yeah, bigger Hecker algebras. Got T sub V. So this is, let me not try and squeeze it in here. I'll go to a new board. Well, maybe I should say, yeah, that's the end of the proposition. That's the statement of the proposition done. And the last thing I'll do is just define this bigger Hecker algebra. So remember we had T, it was a localized Hecker algebra. Acting on cohomology at level K, localized to M. So now we're going to do T sub V. And again, it's going to be an image of a abstract Hecke algebra. So now we'll look at the spherical Hecke algebras away from S and V. Because now we've got some non-maximal level at V. But we have some extra Hecke operators called diamond operators coming from our group delta V. Okay, so that thing is going to act on our cohomology at level I primed V, or the homology. It doesn't matter. You can sort of take the dual or not as you wish. But let's do it with the dual. So. Okay, so that's TV. It's going to be a finite O delta V algebra. And it's going to map surjectively onto T. So that's going to be our sort of first enlargement of the Hecke algebra T. That was a definition. Of this thing. Okay, so that's it for today. That's something about enlarging these Hecke algebras. Patrick will speak next about what happens on the Galois side when we allow ramification of auxiliary sets of primes. Thanks.